There we are. So starting a new chapter, we're kind of done with all of our warm-up, or our introductory material, I should say. It took us a few weeks to kind of get acclimated. And now that we're ready to roll, here's where the rubber meets the road, okay? We're really going to pick up steam with Chapter 2. We're going to start by solving some equations today. And as we go through this material, some of it might be familiar. You might have done a little bit of this, but this is we're really building the groundwork for everything that we do this year. So in this warm-up, you'll notice we're making use of some properties, some techniques that we studied in the last chapter. So this shouldn't be anything too difficult. I'll give you about another minute to work on this, and then we will discuss. Took the mountain bike team up to Nashville this week for a little adventure. Had a good time. Rode some trails, hit some downhill jumps. It's pretty sweet. Crashed once, but it wasn't too bad. And then we got to eat some good catfish while we were there. So it's a classic win-win right there. Alex, classic win-win. Paul, are you a fan of the fried catfish? You like catfish? Not really. What about you, Joe Edwards? You like catfish? Okay. A little bit. Is anybody in the house like just a rabid catfish fan? Anybody like just give me some fried catfish and hush puppies and I'm happy? Oh my goodness gracious. Boys don't know what you're missing. Are y'all aware there's this thing called Cat Mac at CBHS? That is pretty popular. I know Luke knows what that is. Catfish and macaroni and cheese. It's oftentimes a favorite meal of the Christian Brothers student. All right, let's see. Quentin, you got number 1 done, bro? No? Oh my goodness. Well, let's see if you can figure it out. We're going to make use of a property here. Okay, fellas. Charlie, help me name this property. Very good. Now, the distributive property says if I've got a multiplication that's being done on the outside of a group, that I am to do that operation. I'm to multiply times everything in that group. Okay, imagine that we're back in the land of 2019. Okay, we're 2019 where people passed back papers. Okay, suppose I've got a big fat stack of papers right here, and I'm going to distribute them to the class. Everybody gets one. Okay. So if we're going to multiply 3/2 times this polynomial that's in parentheses, then I'm going to multiply 3/2 times 12x. That's the first term. And I'm going to multiply 3/2 times 20. That's the second term. Okay. So what does that wind up giving me? Well, 3/2. What's half of 12, Quentin? Triple that. Bingo. So we got 18x. That's 3/2 times 12x. And then the same thing. What's half of Mossy? What's half of 20? Triple it. And that's what we got right there. So 18x plus 30. That's 3/2 times 12x, and that's 3/2 times 20. Now, if you'll remember, just a little sidebar, since I'm getting some looks, if you'll remember, when we're multiplying a fraction times a non-fraction, that non-fraction, okay, can be written as a fraction just by dividing it by 1, right? Whoops, I put a plus sign instead of a minus, or a times sign, pardon me. And there we go. That's what we want to do. All right, so we're saying 3/2 times each of those. And what I asked Quentin to do was to say, all right, what's 12 over 2? And he said 6. And then I said, okay, triple that. In other words, let's do 3 times 6x, where we got our 18x, right? And then I asked Mossy, hey, cut 20 in half, and he got 10. I said, okay, triple that. And we said, okay, 3 times 10. That gives us that 30, okay? So that's what property, class?
Distributive.
Distributive property. That boy, who was it that came in late on that one? Maybe Josh. Well done. Can you guys hear me okay at home? Y'all give me a thumbs up if you can hear me pretty well. Okay, good. Now, second one's just another example of the distributive property. Jake, what am I distributing in the second one? In the number 2, second example. I don't see a 3 there. Oh, how now, brown cow? We got to follow our order of operations. Okay, so check this. If you didn't hear what Jake was mentioning, it's a good point to bring up. Right here, what operation is that? It's addition. Okay. Now, what operation is going on right here? There's an implied multiplication. All right. There's an implied multiplication. Anytime we see two things sitting next to each other with parentheses, like they're sitting right next to each other here, the -2 and the quantity n plus 1. What's implied that we're doing as far as the operation is concerned? We are multiplying. Okay, so which one takes priority in our order of operations? The addition or the multiplication? All right, we're going to multiply first. Okay, so make those adjustments as needed. So we're going to multiply -2 times n. We're going to multiply -2 times 1. And the 5 just kind of gets put on the back burner. Okay, the 5 just kind of gets put on the back burner. So I've got my 5 leading off. And then I think, Jake, I'll kick it back to you. What's -2 times n? -2n. And what's -2 times 1? -2. Perfect. So after we've done that distribution, now we got all the cards out on the table. Let's see which ones pair up. Okay. Which ones, Tiago? Pair up. I'm looking for two like terms. So which two go together? You told me -2. What goes with that -2? Not really. Okay. Why do not these two terms go together? I'll throw it to Joey at home. Joey, why can't I put those two terms together?
One has a variable.
And the other does not. Very good. Like terms, correct? Like terms require two things. Like terms require same variable raised to the same exponent of power. Yeah, exponent. Lewis, good job. So these two aren't like terms. So I'll throw it back to Tiago again. What do you think? Which two do you want to match up? The 5 and the -2. So what we want to do is we want to put these two guys together, and we can use the commutative and associative properties of addition to say, you know what, let me, and this would be something, by the way, that you would do in your head, okay? Let me say, all right, I can reorder this and say 5 minus 2 minus 2n. We just switch the order of those last two terms, and then we say, all right, let's group these two together. We get 3 minus 2n. I can't do anything else with that 2n, or the two terms, excuse me, because they are not like terms. Okay. This is good. This warm-up is allowing us to discover some areas that we can improve in. Okay, so like we're using the distributive property. Good. And we're talking about like terms and combining like terms and following order of operations. These are all good things. We talked a little bit about multiplying fractions. That's nice. How about the LCD? Let's see if, let's see here, Mr. Kozlowski. Colin, you got a LCD for me? Colin, you with us? Did you get to number 3?
I don't.
Okay, so you see the fractions here are 5/6. All right, there's our first fraction, 5/6, and 1/4. Okay, now number 1, these numbers are small enough such that we can use inspection. Okay, we ought to be able, class, we ought to be able to eyeball it and just tell that the LCD is going to be 12. Okay, but fear not, we've got a process by which we can also find the LCD. Alex is going to walk us through that process. Alex, what did we say to do when you want to find the LCD? Step number 1. Well, that's kind of reiterating the whole notion of the LCD. When I'm talking process, all right, here's what I'm talking about. Oh, it's loading. Oh, we're cooking. We're all loaded up. There we go. Do we remember our process? Well, if not, I ought to have heard when I asked Mr. Cano about LCD, I ought to have heard little papers rustling in the background. I ought to have seen people turning back to their notes on this section because that's where we've gone through. So our first step will be find the prime factorization of each and then circle each new factor raised to the highest power. And then the least common multiple or least common denominator would be the product of everything that we've circled. Okay, so you don't have to write that down because we've already written it down. Therefore, let's use this here. And let's see here. Drew, give me the prime factorization of each of those denominators, please. All right, I'm going to say 2 times 3 because I like to list them in ascending order. And then for the second one, the 4? 2 squared. Okay, so I've got my prime factorization. James, what do I do next? I don't multiply yet, you silly goose. You guys awake today? Y'all are giving me all kinds of wrong answers. And wrong answers lead to right answers, so I'm cool with that. But I want y'all to be on the up and up here. We look at each new factor. 2 is my first new factor. It's raised to the highest power over here, 2 squared, so we're going to circle it there and move on. 3 is my next new factor. Nowhere else is it raised to a higher power, so I'll circle it. And then I get to my last one. I've already dealt with that one, so we're done. LCD would be 3 times 2 squared, which happens to be 12. So my LCD equals 12. Now, I got to be honest with you, fellas. I would be a little bit disappointed if you weren't able to use inspection and eyeball it and see that the LCD is 12 when you're considering the numbers 6 and 4, okay? Now, I'm going to take this a step further. We got 5 6, we got 1/4. 5 6. I'm going to say, let's subtract 1/4, okay? So, Luke, what does that first fraction need to become if I want its denominator to be 12? Good. So 2 on the top, 2 on the bottom, and it becomes 10/12. Okay, it becomes 10/12. And then Reed Johnston, what about that second fraction? What does it become?
3/12.
All right, because I'm going to multiply by 3 over 3, another clever form of 1. So we got 3/12, giving us 7/12. Now, y'all been doing that since the 5th grade, okay? And so when we start seeing more complicated problems, when we start seeing things like instead of 6, when we start seeing denominators like 6x minus 5 and 4x squared plus 3 and things like that, when the issues start becoming more challenging, we've got to rely on what? We've got to rely on our background. We've got to be able to remember ASAT. What in the heck is ASAT, Charlie? No, that's ASAP. I know it's hard for me to pronounce what this ASAT. You know what ASAT is, Josh? Or excuse me, James? See, this you shouldn't, because I've never said it in class before, and it's not a widely used acronym. However, you guys should all remember after today what ASAT stands for. Okay? It stands for all the stuff all the time. You are responsible for ASAT. You are responsible for knowing everything we've talked about since day number 1 and being able to use everything that we've talked about since day number 1. And that's a daunting task, isn't it? Because like if I looked at, let's see here, visual reference. Yeah. All right. So you guys at home can see this. I got a little prop. Right? Got a garbage can. So if I've got this garbage can, and every day in this class, this is perhaps a poor figurative metaphor here, because you wouldn't be considering my class garbage, would you, Quentin? That's right. But like every day, let's imagine we're putting stuff in here. This is our mental basket, okay? And every day, like that little nugget about the LCD, bloop, gets dropped in, okay? Talked about distributive property, bloop, gets dropped in. All right. When we go through and we talk about solving equations today, a definition, I'm going to give you a hardcore definition of what it means to solve an equation. Bloop, goes in the bucket. And then every day, you ought to be able to dig around in this bucket, and pull out what you need when you need it. And then, boop, put it back in there. Okay? That's all the stuff all the time. And when you're in high school math, especially in next year, if you guys, if you go on to take honors geometry next year, it's like amplified how important ASAT is, because geometry is an axiomatic study where you build upon. So like in algebra, we might talk about one topic and we might put it on the shelf and not use it for a couple months. Like in geometry, you talk about a topic today, and then you use it tomorrow to develop something, and then you use what you develop tomorrow to develop the next thing, and to develop the next thing. So it's all the stuff all the time. Okay. So you guys are responsible. So like when we go through little warm-ups like this, brother, don't forget how this stuff works. Okay. Distributive property, heck yes. Adding fractions, please. More, thank you. Okay. All this good stuff. Any questions on the warm-up? We got some glaring areas I think that we need to work on. And any questions you'd like to ask at home or in person? All right. Y'all ready to rock and roll? Let's look here. Now, don't write all this down. Just as I'm talking with you, kind of read through, peruse this step-by-step process. This comes from our textbook. You can copy it down from the textbook if you're reading kind of on your own. But the notion of solving an equation, it grinds my gears when we talk about solving equations. You shouldn't be looking down. You should be looking here and reading. And your little ears should be actively listening and soaking in what we're doing. The notion of solving an equation, people get confused. They just think you can just solve anything, okay? Like if I wrote up 5x plus 3x, and I said to a typical 8th grade algebra student, hey, what do I do here? And they're like, oh, you solve that. No, you don't. Did you see an equal sign? No, then you didn't, quote, solve anything. You see, solving an equation is when you have an equation to begin with. An equation is where you state the left side, the right side, and you put one of those little symbols in the middle that means these two are the same. That is an equation, okay? Now, I told you I was going to give you a hardcore definition. So prepare to write something down verbatim. Latin scholars in the house, what does verbatim mean? Y'all had never heard the phrase verbatim? Wow, y'all are learning all kinds of stuff today. That's excellent. Verbatim pretty much means word for word. In other words, don't paraphrase. Write down exactly what I'm about to say. Verbatim, okay? To solve an equation. To solve an equation is to find any and all. All right, so again, I'll start. To solve an equation is to find any and all of the numbers. So to find any and all of the numbers that when plugged in. Now I'm going to pause just for a second. A little side note here. You don't have to write this down. When I say that when plugged in, I'm talking about substitution, right? When we plug something in, you'll oftentimes hear me say plug and chug. So plug in means to substitute in place. All right, so let's continue. To solve an equation is to, what did we say? To find any and all of the numbers that when plugged in. Okay, so continuing on now, we'll plug in for the variable. And then at the end of the word variable, can you put S in parentheses? You know what that means? Yeah, good. We're maintaining the possibility of singularity or plurality. So in other words, that word could be singular or plural. It could mean variable or variables. Because aren't there sometimes you see equations that have multiple variables in them? Sure. So we're at this definition, we're accounting for that possibility, okay? So it means to find any and all the numbers that when plugged in for the variable or variables makes a true statement. Okay, makes a true statement. Actually, the word should be make grammatically. correct. I think it should be make. But what do we care? We're not grammarians in this house. We're Algerians? No. Algebranians? All right. So here's the rundown. That definition has three main parts. The first part is that when you're solving an equation, you're looking for a set of numbers. That set might be empty. You might have an equation that has no solution. Okay. But you're looking for a set of numbers. Okay. And the goal is to be able to plug in those numbers for the variables. Okay. So we're using that substitution principle. And then we want to be able to make a true statement. Okay. Like check out step 5 here at the end. This is the one that oftentimes gets overlooked. Okay. And so you guys will see throughout the course of this year, you will encounter some equations where you might follow this kind of step-by-step mantra here. You might go through and you might do everything that I've asked you to do. And then at the end, the answer that you get actually is a fake answer. It doesn't actually work. Okay? And you might be inclined to like circle it and say, here's my answer, Coach Morgan. And I'd say, wrong, because you didn't do this 5th step. You didn't double check to make sure that the number that you found when you plugged it in made a true statement. Now, I know that sounds kooky, but there are some kooky stuff, equations that we encounter in this class, all right? And we'll talk about how those fake solutions kind of come about. But, you know, this first one we're going to deal with is just a nice, plain, simple equation, okay? This is an example of what it looks like to solve a basic equation. And you and I are going to walk through a process together. We're going to do this one together, okay? I'll show you exactly what to do. Now, we've got options, and I don't like to create little math robots, okay? I'm going to open my window while I'm talking. I don't like to create little mathy robots. You guys are going to be, you're going to do what you want to do, and I'll be flexible, and I'll be willing to accept that not everybody works a problem the way that I would work a problem. All right, like, so for example, Chuck back here might want to say, yes, I'll distribute that 5 times a minus 3. And some of you might very well agree with him. Nate at home, on the other hand, Nate might say, no. I'm going to divide everything by 5. Okay, and both of those guys could be right. You can get the right answer going that way. Either way, okay? So what we need to do is we need to, first of all, be consistent. We need to find an approach that works for us individually and stick with it, okay? But at the same time, we also need to be versatile and understand that sometimes there's more than one way to attack a problem. And my normal way of doing things with which I'm consistently approaching problems, in one or two particular aspects, it might not be the most efficient approach, okay? If my approach to fix something is to get some WD-40 and a hammer and go to whacking on it every time, okay, that works sometimes. But that might not always be the most efficient route to fixing something. And I need to be versatile. My hammer doesn't need to be my only daggum tool. So check this out. Here's what I would recommend doing in this case, okay? I would use inverse operations. Can you write down that phrase, please? Inverse operations. All right. Now, what the heck are inverse operations? Anybody got an idea? Mr. Oxley. All right. So if you didn't hear what he said, I liked what you said, but I didn't like how you said it. Okay. So let's adjust things just a bit. So you use the word opposite. Let's not use the word opposite because I know what you mean, and you're right with the way that you mean it. But the words inverse and opposite are not the same thing, okay? So like what he was talking about was addition and subtraction. They undo each other, so to speak, okay? Like Mossy, I don't got any cash on me right now, but let's say I did. And I whip out a $20 bill and I go, hey, Mossy, here's 20 bucks, woohoo! And then a couple seconds later, I go up to Mossy, hey, Mossy, can I have $20, please? And he gives me $20, okay? He's back to square one, isn't he? We hadn't changed the daggum thing. So plus 20 minus 20, those are inverse ops, okay? If I went up to Ben and I said, Ben, I'm going to triple the amount of food that you get to eat today. Ben's like, woohoo! And then I say, oh, wait a minute, you know what? Take that new amount. Let's let's cut it down by a third. And he's like, he's back to square one. So what are our inverse ops? Addition and subtraction undo each other. Multiplication and division undo each other. Squaring something and taking the square root undo each other. Okay, and for right now, those will be our basics. There's other inverse operations. There's a boatload of them. All right, but in algebra, you know, these are kind of the ones that you basically encounter early on. Okay, so the notion of using inverse ops is like peeling an onion. Okay, you guys ever seen the movie Shrek? You know what I'm talking about, Shrek? Okay, I let my kids watch Shrek a couple years ago, and they liked it. And then I realized there's a lot of jokes that are in Shrek that go right over the head of a 5-year-old. But there's a quote from Shrek where he says, ogres are like onions. They have what? They have layers. And an equation is much like an ogre, which is much like an onion. It's got layers also. If any of you guys cook, you guys do any kind of cooking? Some of you guys do, okay. Let's say, Mossy, do y'all make Italian food? Okay. Like let's say we're gonna make some sauce, okay? What do you call it? Bolognese? Yeah, like a good old-fashioned spaghetti sauce. All right. In my spaghetti sauce, I like to put a little bit of some onions. Okay. And let's say I get out my onion. Do I just go ahead and chop it up and throw it in there? No, because if you've ever picked up an onion off the shelf, what's it got on it? Oh, it's got this nasty, dry, crunchy outer layer. Blech, and that would make for a leathery, gross bite from my spaghetti sauce. Okay. So instead, we peel the onion. We get to the juicy inner core, and that's what we like to cook. Okay, same thing with like you know, shallots and garlic and all those types of vegetables. Okay, so with this equation, what's my quote outer layer? Well, think about the A, and let's consider our order of operations in reverse. Okay, so in other words, the first thing that's being done to that A is to subtract 3. So we're going to deal with it last. The next thing that's being done to that A is there's a times 5. We're going to deal with that next to last. And then the final thing that's being done to that A is a plus 5, and we're going to deal with that first. That's the outer layer that we want to peel first. So what undoes, Paul, a plus 5? A minus 5. So let's subtract 5 from the left. Now, let's write down a quick little rule here. This is uber important. Muy importante in Espanol. All right. Whatever I do to one side of an equation, I have to do to the other. We got to keep things balanced. The notion of the two-pan balance comes to mind. If you've ever been in science class before and you guys are weighing something in a little two-pan balance, or if you've seen Lady Justice, right? What's she doing? She got a big old blindfold and she's holding up some scales. Okay, a two-pan balance, if I put something on the left side, I've got to put the same amount on the right side to balance it out. If I take something away from the left side, I got to take the same amount away on the right to balance it out. That's how an equation works. So if I say, let us subtract 5 from the left side, I must also say, let us subtract 5 from the right side. And that cancels out that 5. That's that inverse op right there. And what are we left with? We're left with 5 quantity A minus 3 equals negative 15. Okay. Quentin, what do you want to do next? What inverse operation might suit our needs? Think about that second layer. We want to get rid of that 5. What are you going to do to get rid of that 5? All right, I don't want to subtract. What operation is being done between that 5 and that parentheses? What do you think, buddy?
Since there's a multiplication sign, you divide the 5.
Bingo. Did you guys hear what he said? He said, since there's a multiplication sign, we want to divide both sides. Because that's that inverse op, plus, minus, multiply, divide, all that good stuff. So whatever I do on the left side, Quentin told me, hey, Coach Morgan, divide both sides by 5. Tiago, what does that mean I also have to do? Divide the right-hand side by 5, okay? So what am I left with on the left-hand side? A minus 3 equals negative 3. Okay? And then last but not least, Alex, take us home. What do I do to both sides? I want to get A by itself, right? I'm peeling back these layers. Sometimes textbooks will say, hey, you want to isolate the variable. We want to get A by itself. So what's going to undo that minus 3, Alex? A plus 3. Let's add 3 to the left. And if I add 3 to the left, balance it out for me. What do I also have to do? Add 3 to the right. Yes, sir, Bob. All right, so minus 3 plus 3 is going to cancel out. And look at what I'm left with. I kind of ran out of room right here. I got A on the left side. It's by itself. What's on the right-hand side? 0. Is it okay to have an answer of 0, by the way? Daggum right it is. Okay, sometimes we get an answer of 0, and that's okay. Now, what should I do at the end of the problem? Check to make sure, because the definition of solving an equation means to find any and all of the numbers that, when plugged in for the variables, make a true statement. Okay, I found A equals 0. Now I need to plug that back in. We can do this mentally. Okay, we can do this mentally. So we take and we say, all right, A equals 0. So that means 0 minus 3 is negative 3 times 5 is negative 15, plus 5 is negative 10. And we just follow our order of operations in the proper order now that we're plugging it back in. 0 minus 3 is negative 3 times 5 is negative 15, plus 5 is negative 10. It checks out, left side equals right side. Therefore, that is our solution. Okay. Have you guys done any equation solving in y'all's classes yet at this point? I've done a little bit. Okay. So the idea of solving equations is that you can just practice the heck out of it. Okay. So I'm going to give you guys some practice on deltamath.com tonight. I will post it up there probably this morning sometime. So when you get home and you start doing your homework, just log into Delta Math. You'll see a new assignment. It will be titled 2.1, Homework 2.1, and you guys can rock it out on there. Okay? If y'all have any questions for me, either in person or at home? All right. You fellas have done a great job. Live Jesus in our hearts. Thank you very much, and I will see y'all on Thursday. See you guys on Thursday. Do, 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 do.